So in this chapter, we are learning about acids and bases, and we're learning more about them. So you probably learned about them in Chem 1, but what we're going to do now actually is apply what we learned in the equilibrium chapter, so the previous chapter, to acids and bases. So most acid-base reactions are in equilibrium. So because of that, there's a lot of, equilibrium concentrations. We can relate that back to pH. There's a lot of different calculations we can do. So this is kind of a heavier chapter with calculations and applying previous knowledge, in other words, the previous chapter to it. But just like I always say, take it step by step. But first, we're starting off in a pretty softer way. So we are just refreshing on what acids and bases are. And just to give you a real life context about acids. So in your stomach, hydrochloric acid is produced, which is insane to think that we have this really harmful outside of your body, obviously. If you have strong concentrated hydrochloric acid and it lands on your skin, you would have this really nasty burn. And if you didn't wash it or treat it, you could have further damage in your tissue. But when you produce HCl, we produce HCl to kill bacteria, to help break down food, to activate enzymes that break down food, for a bunch of reasons. Now, if you happen to eat stuff that kind of perturbs the equilibrium of your acids in your stomach, then you're going to get acid reflux. So it's going to come back up, right? So for me, when I eat a lot of hot Cheetos, I'm really happy during eating hot Cheetos. I'm like, yes, this is amazing. I love hot Cheetos. But then later on, I get reflux. And if you've never had reflux, it's horrible. And what you can do is take antacids to neutralize it. So what you're actually doing when you're eating hot Cheetos and then eating Tums, like how I do occasionally, as I get older, it gets harder to deal with, so I don't eat them as often. But whenever I do make that bad decision, I always follow it with Tums. So what I'm doing first is eating a bunch of acid and then eating some base to neutralize it. So if you do that and you're like me, that's what you're doing. You're increasing the concentration of an acid and then you're neutralizing it with a base, with a Tums. So some general properties of acids: they are sour, yummy hot Cheetos. They can also obviously do some really gnarly things. They dissolve many metals. They can neutralize bases, obviously. With litmus paper, it goes from blue to red. So some of the cleaning ones are HCl, also HF, a few other ones. And then something more common that you deal with is acetic acid. So vinegar, you can use it. Vinegar has acetic acid. You can use it to preserve food. When you learned about naming acids in Chem 1, you learned that there's two. We have binary acids and oxyacids. Binary acids have hydrogen and a halogen. Even though we don't say it's a nonmetal, it's usually a halogen. Oxyacids have hydrogens and a polyatomic ion that has oxygen in it. So a polyatomic ion like sulfate, polyatomic ion like nitrate. We also have another type of acid called carboxylic acids. You haven't learned about these just yet. If you take organic chemistry, you will learn about carboxylic functional group. Well, carboxylic acid functional group. For carboxylic acid groups, we have COOH, and it's this structure right here. So you have to have this particular structure to have a carboxylic acid. It can have whatever necessary or possible on this other end, right? This isn't a full molecule shown right here. This is just the group, the functional group. Only this H right here is the acidic H. It's the one that's going to come off and react with whatever else is in solution. So citric acid, which is just the acids in citrusy fruits, so limes, oranges, all of those, is actually a carboxylic type acid. Bases are different from acids, obviously. You can think of them like the opposite. They taste bitter in comparison to sour. They are often poisonous, so it's not as common for us to be like ingesting bases. Like with vinegar, we eat pickles, right? Which is acetic acid. With citric acid, it's in our fruits. Things like that. It's very common to have acids in like food. Obviously not in high concentrations, but with bases, it's a lot less common. Something that is common is sodium bicarbonate, for example, antacid, baking soda, but it's not necessarily like a food, Some other common bases are sodium hydroxide, potassium hydroxide. These are used for like manufacturing, processing. Ammonia, we all know about ammonia and how it's in Windex. Hopefully that's what gives it that like terrible smell. So it's like it's a detergent, or I was going to say a cleaner, but same thing. Bases feel slippery. They turn litmus paper the opposite, so red to blue, and obviously they neutralize acids. So I've talked about like very qualitative things about acids and how you see them in your everyday life, common examples, but what is the actual theory behind acids and bases? And you probably learned like a very, very general version of this in Chem 1. But we actually use the Bronsted-Lowry definition for acid-base theory. So the Bronsted-Lowry acid-base theory is that any reaction involving H+, meaning this is something we call proton, that transfers from one molecule to another is an acid-base reaction. So this is like the main requirement. You have to have a proton being transferred from one thing to another. So the acid is the one that gives it up. That's why it has to have an H in it. And then the base is the one that accepts it. And specifically for the Bronsted-Lowry definition, this will happen in aqueous solution regardless whether you have OH or not. Now, commonly, you will have OH. Many bases have OH, but it's not required, okay? The only requirement is that you have that H+. In the Bronsted-Lowry acid-base reaction, your acid, right? This is just a general notation for having the acid. The H part is the requirement, remember, will react with your base, and then you'll have that new product, and then you'll have the other part of the acid just kind of like on its own now, right? So they switched places. Hopefully you can see that. Something that is required for the base is that it has to have an unshared pair of electrons on one of the atoms, so that it can take that H+. So you see how this has an unshared pair of electrons, or a lone pair? That's what takes that H+ and reacts with it, and it forms that bond right there. So here's an example. We have HCl reacting with water, for example. And in water, hopefully you remember the Lewis structure. This is how it looks. We have two lone pairs on the oxygen. So the requirement, remember, for an acid in a Bronsted-Lowry definition is that we have an H being able to be donated from the acid, and then a lone pair somewhere on the base. So in this particular case, we know we have some lone pairs on the oxygen, and this is the part that actually reacts with that H, takes it away. You end up having H3O+, and then that chloride ion is on its own in solution. So now what about the opposite? We have Bronsted-Lowry bases, right? Bronsted-Lowry bases by definition are just H plus acceptors, right? That's all, the only like requirement. And it has to have that lone pair in order to take it. So in this particular example, we have NH3 acting as a base. We know that NH3, the Lewis structure is like this. It has a lone pair on top of that nitrogen. It's not drawn very well, but you get the point. It has a lone pair, so that means it can accept that H plus. So here we see that it takes, right, there's a lone pair, takes one of those hydrogens, it forms NH4 plus, and now we have OH in solution. There are certain substances that can actually act as both an acid and a base. These substances we term as amphoteric. So that means they can act as either. So think of how like someone is ambidextrous. They can write with their left hand and their right hand, or they can, you know, they don't have like one dominant hand. They can do things with both. That's how amphoteric substances are. So they can act as a base and as an acid. So for example, water, it can act as a base. So in this case, it was acting as a base. And in this case, it's acting as an acid. And it can do both things. And there are other substances that can also do this. And this is due to the fact that one has a transferable H it can give away. So here it gave away one of those H's. And then here it accepted an H or a proton because it has a lone pair. So it has to have those two things. It can have a transferable H, meaning it can give an H away, a proton, and it can accept a proton because of a lone pair somewhere. So the Bronsted-Lowry theory is useful is because it can show us how this reaction, or not this reaction, but acid-base reactions, how they can be reversible, and how like on one side, let's say the reactants, we have an acid and a base, and on the other side we also have an acid and a base. So just to show you, here we have an acid, right, and we have our base. They react and they form our products. So this base accepts that proton, you get HB, and then the other part of the acid just, you know, is in solution. Now if you look at it the other way around, so down here, and this is just flipped around, that's all it is, we have our base, right? So this is our original acid and our original base. Now when you look at it the other way around, this can act as a base and this can act as an acid. So this is an advantage of this theory because we can illustrate these reversible reactions. So there is actually a name to this idea, the fact that if we have a reaction go one way, you know, we start off with an acid and a base, and then if you look at it the other way around, we have an acid and a base also in solution, right, on our product side. So the name that we give to these products are conjugates. So for our original acid, we end up having a base that is kind of like its little pair, right? So our original acid is right here, H2O. And when you take off that proton from it, you get its conjugate base, which is OH minus. So the conjugate base is what you have left over from that original acid, acting as an acid, giving away its proton. For the original base, what you end up getting as its little pair is a conjugate acid. So we started off with NH3 acting as a base and accepting a proton, and what you got from that was NH4. Now this NH4, if you go this way, it will be acting as an acid, so it's the conjugate acid. So in a Bronsted-Lowry acid-base reaction, the original base becomes an acid in the reverse reaction. The original acid becomes a base in the reverse process, and they're each called their conjugate, and these are conjugate pairs. It's covered up. I don't know what happened with me rendering this as a PDF, but These are conjugate acid-base pairs. Here, this is just showing you another example. Here we have HF acting as an acid, and then H2O acting as a base, accepting protons. So here you can see that H2O accepted that proton coming from the acid, and now it is a conjugate acid. And then the base over here is now just the fluoride ion in solution, and now it is the conjugate base. So finally, we end off this particular video with discussing strong versus weak acids. So strong acid is a strong electrolyte. And acids, what happens whenever they are turned into acids, because originally you start off with molecular compounds. So for example, let's say HCl. It starts off as HCl gas, and then once it goes into water and becomes aqueous, what actually happens is that it ionizes. So in solution, how it actually looks, right, is H plus and Cl minus. This process, the fact that it's like splitting up, is called ionization. Strong acids ionize 100%. So they completely turn into their ion versions, okay? Same thing happens with strong base. All of the base molecules will dissociate into OH minus. In comparison to weak acids and weak bases do not completely ionize or dissociate the way that strong acids and strong bases do. So weak acids and weak bases, only a small percentage either ionize for acids or dissociate for bases. And just to show you visually how this looks, strong acids donate all of their H's, meaning it completely splits up. So once you put HCl, this is what I was talking about earlier, when you dissolve it into water and make it an acid essentially, it completely splits up into the H, the protons, and the chloride ions. So it's 100% ionized in water. It's a strong electrolyte. Here we have weak acids. Weak acids only donate a small fraction of their H's. So let's say we dissolve HF, hydrofluoric acid, into water to make it an acid. Not all of it is going to ionize. Not all of the protons will ionize away from the fluoride ions to get, H3O, right? Anytime you see H3O or H+, this is in reference to concentration of acid. So instead what you see is a mixture, right? You see some HF still intact, you see some fluoride ions, you see some protons that reacted with the water in solution. So this is because not all of these donate their protons to water. Not all of the weak acid molecules do that. So you have less than 1% ionized in water, and overall this is a weak acid. These are the strong acids. There's 6 strong acids. And then anything else besides these 6 strong acids are considered weak. So that's why there's just some illustrated right here, but anything else not on this list of the 6 strong acids is basically weak. We can also determine acid or base strength by measuring the equilibrium constant, right? So remember, equilibrium constants allow us to determine, okay, how much product versus reactant do I have? If I have a big Kc value, that means I have a lot of product on that numerator, right? Allowing you to calculate that really large Kc value. So the farther the equilibrium position lies towards the products, then the stronger the acid or the base. So larger Kc, that means stronger. That's horrible handwriting. Stronger acid or base. So the position of equilibrium depends on the strength attraction between the base and the H. So a strong acid will completely ionize. It doesn't care about staying intact as the original acid. So let's say we have H and then Cl, right? Or proton and our Cl. HCl don't care about each other. They want to split up as soon as they get into water. They're completely okay with that. Versus weak acids, they want to stick together. So they're not going to completely ionize the same way that a strong acid would do. Finally, we have some general trends in acidity. So the stronger an acid is at donating H, the weaker the conjugate base is at accepting it. So the fact that the conjugate base doesn't want to accept that H means that it'll stay on the products, like the equilibrium will stay shifted towards the products, and it's not going to move because the conjugate base is like, no, I don't want that proton from that conjugate acid. So it just stays, like it would just stay on those products and not shift the other way back. And then in terms of these oxyacids, so here we have sulfuric versus sulfurous acid. So this is sulfuric, this is sulfurous. And then we have nitric versus nitrous acid. So in these acids, what's different is the amount of oxygens you have, bonded to these central atoms in those polyatomic ions. So these central atoms have different oxidation numbers, and I actually went ahead and wrote the oxidation numbers for these atoms that I have circled, and you can see here that H2SO4, the sulfur in it, has a higher oxidation number, +6, and over here it's +5. Sulfuric acid is stronger, nitric acid is stronger. So the higher the oxidation number, the stronger the oxyacid. We also have this trend where we look at a cation versus a neutral molecule and then an anion. The cation will be the stronger acid out of the three. So here we have two sets, right? So split it down right there. First we have the water family. So H3O, which is a cation, is a stronger acid in comparison to H2O and then OH. The reason for this is again because of the definition of Bronsted-Lowry. Bronsted-Lowry base definition says you have to have a lone pair. So on that OH minus, we actually have a few lone pairs. We actually have 3 lone pairs. So because of that, it would make it a stronger base, not a stronger acid. So H3O over here has extra H's, extra protons to give away. It's like, yes, I want to give it away. Here you go. So that's why it's the strongest acid. That's why you have that sign right there. H2O is in the middle, and then OH is like, I don't want to give away another H. Do you not see me hanging on for dear life with this last H? Please give me an H. It's the opposite. It's the base, right? And same thing here with ammonium versus ammonia, and then this would be an ion, which I can't remember off the top of my head right now, but this one wants to give away one of those H's. It's like, here, take one, and then NH is kind of in the middle, and then this one's like, no, please don't take away any more of my H's, any more of my protons. So that's why the trend in the base strength would be the opposite.